This video is to help us with chapter 1.5, finding the derivative, kind of using shortcut rules that we talked about in class. And so I want to go through some of those examples and some of the maybe the quick checks so that could help you with your homework. First, we got to remember what a derivative is. And so when looking at what we're talking about here again, first we introduce the derivative, right, using this notation here, using the what we call the f prime notation here. And so that represents the derivative of the function f. And again, remember what a derivative is. All it is telling you the rate of change, the instantaneous rate of change of a function, right? And so just to have that quick reminder. So if you have some function, right, a graph of it, and so the best way to kind of look at a derivative is through kind of a graph. And so let's say you have a graph like that, and then let's say this x value is, let's call that 2, and then someone is ask you, what is f prime of 2, given that this function here is f of x. What we're really asking you graphically, not the algebra, but graphically, what we're really asking you is at this point, f of 2, how fast is the y value increasing? And the way we do that is we approximate that with a tangent line right there. And so the slope of this tangent line, is what we would say f prime of 2. Whatever value that is, going to be a number, and see how the slope is going up, so this answer would be positive. So that's what it's asking you when it's asking to calculate a derivative. And now all we're doing in this section is looking for shortcuts, and we do algebraic shortcuts. And so that was some of the rules that we started looking at in class. And to help us with it, we also have a different notation, dy dx. Those two are the same idea. This is the derivative of y with respect to x. And so many times we have equations as y equals. And so an example here then, if I had y equals to x squared, then dy dx would be equal to 2x based on our rules that we had kind of talked about. But just want to remind you of that. So the first rule is the power rule, where we looked at the shortcut to calculating derivative is again through looking at when it's in a polynomial form. All we do is take the exponent, put it in front, and then reduce the exponent by 1, and that's the shortcut of finding the derivative. And so again, why the rule works is it's just based off of patterns that we observed over time of using the limit kind of rule on 1.4. But here we're looking for shortcuts to do that. And so we talked about these examples in class. If we had these here, and so from here you could say the derivative of this function, which is y, here's your y, with respect to x, x being the variable, you can see what they calculate to. And so this one sometimes looks hard to do, because like, what's the derivative of y equals x? Well, we're looking at the x, derivative of y, which is x. The exponent is 1, and so that's where you get just 1. Keep in mind, since this is a linear equation or linear function, right? A linear equation always has a constant rate of change. It always has a slope, right? And so that never changes, and that's why the answer is constant. Always has what we call a constant rate of change. And so what happens is you're always going to get a constant, a numerical value when you take the derivative of a linear equation, constant rate of change. So keep that in mind there when we do that. And then you can see even a negative exponent follows the same rule. Be careful here, it goes to -5 because we're reducing one, -4 minus 1. And so we did this quick check in class already, or I think we left off. So in this case right here for number 1, dy dx is equal to the derivative of x to the 15 with respect to x, and in this case you get 15x 14. On number 2, you end up with the derivative of y with respect to x. Again, we just have it in a different notation here, so that's why it's not f prime, and we're taking the derivative of that with respect to x. And so it's negative 7x, and then subtract 1, so it's negative 8, and so there's your answer. We could have also seen it as negative 7 over 8, x to the power of 8. So that was another way. And this one here is kind of a trick question. Pi is approximately equal to 3.14. And so in this case here, we're taking the derivative. How is that number, the derivative of pi squared? Pi squared is some number, is a constant. And so what's the rate of change of a constant? It's 0. It never changes. So that's why, think about that now, why it's 0. Okay, it's not 2 pi. It doesn't follow because it's not a variable. It's just a number. And so that's what we were looking at there. Here's your quick check solution, the one that we did already. So you can look at the explanation there if you need it for your notes. And so that's the introduction. We're going to go look at some more, but I'll do another video. But that's the introduction to your derivatives.